Qualcomm has been investing in an outdoor OTA network in a headquarters in San Diego for a number of years now to push the technological boundaries of 5G. This is a 28 gigahertz system that represents a real-life deployment and allows us to understand and address real-life deployment issues. This was a network we showcased last year in MWC 19, but have since further enhanced to provide more robustness and coverage. It's a single cell deployment. It's a single GNOB with multiple distributed remote radio heads that provide receive and transmit diversity, as well as fast beam switching across the deployment space. We've also enhanced it with repeaters, Qualcomm prototype repeaters, for non-line of sight coverage and out-to-in coverage. The test device on our network is based on the Qualcomm Snapdragon 5G modem RF system. We have 3 antenna modules for uniform coverage and experience for the UE. Throughout this demo, you'll be seeing this GUI that portrays the KPIs for the demos. We have the downlink throughput, the active and candid beams for up to 2 remote radio heads on the GNOB, as well as the active module and the associated beam pattern for the device. We'll be covering robust mobility, enhanced deployment, as well as new use cases on our network. With distributed remote radio heads, the GNOB has the ability to use multiple remote radio heads to different users or to a single user. We'll start off by showing the capability of spatial multiplexing. So using 2 remote radio heads to support 2 relatively close users without any interference to each other. We can also use these multiple remote radio heads to provide extra robustness as well as coverage for a single user. In this demo, we have a single user, again being covered by 2 remote radio heads, walking towards a courtyard and briefly blocked by a metal van, but without any cut to service because of the other remote radio head. So this level of robustness is exactly what you would need in a real-life deployment, especially when you have a dense number of users or dynamics in the environment, such as in a big square like Times Square. So in this next demo, we'll have a user, again, being served by 2 remote radio heads, the same 2 remote radio heads, walking through a large crowd, dense crowd, and being periodically blocked from either side, but able to maintain the link and able to maintain the experience because of the multiple remote radio heads and the multiple antenna modules on the UE. We also want to show the limits of Release 15 as well as our own beam management algorithms, so the ability to beam switch and beam track our device. We put our device on a drone to have high mobility across our deployment area, as well as show high dynamics by showing rotation of the drone. We saw that even with a single remote radio head, we're able to comfortably support high mobility as well as the dynamics for, again, a uniform experience in the deployment. As we know, millimeter wave, it's hard to get non-line of sight coverage unless you have good reflectors in the space. So you're bound to have coverage holes in your deployment. We show that with our prototype repeater that we can actually overcome this line of sight diffraction loss and provide coverage and extend the coverage area. So repeaters are not only good for overcoming the diffraction loss of going around buildings, but also to overcome penetration loss going from outdoors to indoors. This would be key to provide any kind of coverage in an indoor space, lobby, cafe, or store where you have a high density of users and you want to provide data offload. We've also used our network to test new use cases such as boundless VR extensively to see that we can support the performance needed. We know that millimeter wave systems in terms of throughput and latency are perfect for these type of applications. But we also show that in our new deployment strategy with multiple remote radio heads, we can provide a level of robustness that are key for these immersive experiences. Thank you.